Yeah, no, I have to run.
Yeah.
Oh, yeah. Yeah. Some sort of okay. Yeah, it's basically called. Yeah. No, A for the days, but it's yeah. There.
voor de omega.
Ja, maar Okay, well, so how did you fare? Is there can someone just to kick things off? Can someone give me a definition of the absorption? Just this. What is the absorption efficiency? If you would explain it on a party. Well, I don't recommend that, by the way. What is the absorption efficiency?
Efficiëntie van de hoeveelheid licht dat opkomt ten opzichte van groot.
I want to be a little bit more specific. You had a... Yeah, that would be the most formal way of defining it. So really a ratio of powers, the absorbed power over the incident power. Yeah. Then the absorption cross section. So we now have Q, which is the absorbed power over the incident power. What would then be the absorption cross section? What are the units of the absorption cross section? Yeah, that's an area, that's for sure. And how is that related to the absorbed power? We had the absorption cross-section was the absorbed power divided by the incident power. So that is then, these are both powers, so that is unitless. The absorption cross-section has units of square meter. So can you give some kind of way of calculating it? Yeah. So the absorbed power over the intensity. That's one. You also know about the second definition.
The efficient absorption times
Yeah, of the molecule. Yeah, so QA times the geometrical area of the molecule. So, yeah, and then the last one, the absorption coefficient. So how is that related to the other ones?
Is that mu? Or?
That's mu, yeah. That's een prachtige mu, man.
Sigma A maal rho A.
Sigma A times rho. En wat is rho dan?
The molecular density.
Yeah, so the number of particles per unit volume. Yeah. Then we have them all fixed again. Okay, so I gave you a couple of numbers and a couple of graphs in that assignment. And basically, the assignment was tying them all together to find an absorption coefficient, an absorption cross section, and an absorption efficiency. Actually, in that order for that molecule. Does anyone have any numbers for me? What was the absorption coefficient that you calculated? Yeah, 10 per centimeter. Yeah, that's exactly right. I don't know the other ones by heart, so I'm going to skip through here. Yeah, 10 centimeters. So what you needed to combine here was the molar absorption coefficient that was given. So the absorption coefficient per centimeter per molar, and then we have the typical jaundice concentration. And combining these two together, we end up at 10 per centimeter. Yeah, and then of course once we know that, and we know this molecular density also in the other unit that was also given, then we can calculate what the scattering cross section was, and that's pretty small. It's in the order of 10 to the power minus 16 square centimeter. So that's really small, and this is a little bit hard to. And so we knew that the diameter of the molecule was in the order of 1 nanometer. So we can now calculate also using this last equation what the absorption efficiency is. So what was the absorption efficiency? Did anyone get that number? 1.2%. I'll give you the 0.2. Yeah. So about 1%. So only 1% of the power that is incident on such a molecule is actually absorbed. The rest is just passes along. So it's a really bad absorber actually. So if we now look at so again, so the graph on top is again So the maximum molar absorption coefficient is at 400, about 450 nanometer. And that turns out, so this is again on the other axis, but that turns out to be about 1%. If you now make the same graph for the absorption efficiency for hemoglobin, so for blood, then this is the competition. So at 450 nanometer, the absorption efficiency is about 1. So if the light hits a hemoglobin molecule, it is almost definitely going to be absorbed. So the question is now, can you now imagine how difficult it is to do such a measurement on such a neonate? Because there are these bilirubin molecules, but there's only a small amount of them. They are very less efficient absorbers than hemoglobin, the blood, which is all present. So what you have to do here, the challenge here is to pick out a very small signal over a huge background. So the hint is if you look at this graph, so how can you do that? How can you pick that?
I thought maybe by checking at a higher wavelength what the absorptions of oxy and deoxyhemoglobin are,
yeah,
and then subtract that from the signal at 450 nanometers to keep just the signal from the bilirubin.
Yeah, that's the best and the most straightforward way of approaching it, because you can assume that this spectrum does not change. So making a measurement here is equivalent to making a measurement there. So if you do that at a few clever choices of wavelengths, then they can actually do it. Yeah. That's great. Okay, I want to go into one strange effect with you, and that is the last thing for today. So this you know by now. This is what. Yeah.
Can you repeat the answer to the previous question?
For the, yeah, of course. I'm sorry. Yeah. So the problem for that measurement is that the absorption efficiency of bilirubin is only 1%, whereas the absorption efficiency of hemoglobin is about 100% at the same wavelength. So if you would do the measurement at this wavelength, it would be very hard to get a meaningful result. So the question is, what can you now do cleverly to unmix these signals, basically, and that's what you can do. So you can pick a wavelength where you could pick, for example, a wavelength where the absorption of oxygenized and deoxygenized hemoglobin is the same. So whatever you would measure there is hemoglobin. You don't even have to worry about whether it is oxygenized or not. But you could also say, okay, I know here that the difference is very big, so I could pick that, etc., etc. So just picking a few clever wavelengths and doing the measurement there would help you solve that problem. Yep. Okay, again, this one. So let's. So take a good look at this equation again, at this situation again, at this measurement again. Now suppose that you would have a solution of molecules where you don't know the absorption coefficient. How would the measurement look like?
See how much goes through.
Yeah. So so typically what would you measure? It's a stupid question, but yeah, E and E0, of course. That's what you put in, what you get out, and you would also need to know L. But if in principle, if you would know these three, you could determine mu A. Okay, keep that in mind. Keep that in mind.
Which three? So I0.
So I0 at the beginning, I coming out, and L,
Okay.
and then from this last one, that would give you mu A.
What happens to the?
Okay.
Oh no, you're
Yeah, really. So.
Yeah, what happens to the sigma and the?
Yeah, okay. Okay, that was a little bit overcomplicating it. So let's say let's say that we're primarily interested in mu A. Then these three numbers should be enough. Okay, let's do a thought experiment. So we have still that cuvette, still an intensity I0 that illuminates the cuvette. We can measure what goes in, we can measure what goes out. We know the thickness of the cuvette exactly. We also know the area that is illuminated. And we also know that the molecules are homogeneously distributed in the cuvette. So everything is basically all perfect and physically responsible. So then the question is, and this is the easy one. So what is the transmittance that you would measure in this experiment? So, and transmittance here is defined as I over I0.
The rest of the equation. So the power of E.
Yeah, so, okay, so we have E is E0, and then times the exponential of mu A times L. So if you divide, then that's the exponential. Okay, fair enough. So how? Yeah, Lambert beer. So the next question is, okay, so how would you, and this is also a little bit insulting your intelligence, but how do you retrieve the absorption coefficient from such an experiment?
You write the equation.
Yeah, like I said, it's a little bit insulting, but so you do the measurement, you measure I, you measure I0, then you have the exponential, you take the natural logarithm, you take minus minus that value, and then you divide by the L, the length of the cuvette, and then you get your mu A. That is the process. So if you don't know, and that's my point, if you don't know the absorption coefficient, this is the way that you would have to go to go get it. Okay, finally let's do that thought experiment. So the total number of molecules in that cuvette is given by a certain number density, so the number of molecules per unit volume times the volume. So that is rho, number of molecules per unit volume, times A times L. Now let's say that nothing changes with these molecules, nothing at all. The only thing I do is I move them to the front of the cuvette. So just to show you, here they were beautifully arranged throughout the whole cuvette, and now somehow I managed to move them in the front half of the cuvette. Now the question, of course, is let's do. I don't know the absorption coefficient. I'll do the same measurement. What will I measure?
Your L gets smaller, so maybe your I also gets smaller.
Your L definitely gets smaller. That gets to be only half.
But maybe your density, also increases, I guess.
Exactly. Yeah. So what happens here is that first for the transmittance, and then we'll go to the absorption coefficient. What happens here is that the L is and so everything is pushed to the front. So the L only gets twice as small, but the concentration, of course, gets twice as high. Yeah.
Might be a stupid question, but does anything change at all in that case? Because you would still be left with the rho times sigma times L if you factor out constants.
That is absolutely not a stupid question. The only thing is that you're a little bit ahead of me now, because I'm going to change. I'm going to change the experiment a little bit further. So here, you're absolutely right. So nothing really changed because the two gets crossed out for the half, and and everything is the same. So what you would measure for your mu-A, measurement-wise, would still be, okay, I calculate the transmission, I over I0, that would be T, ln of T, take the negative, and then divide by L, okay, all very and good. But now, let's put all the molecules not to the front of the cuvette, but to the side of the cuvette.
The light still hits.
It still hits the whole cuvette.
Okay.
Yeah. So what happens now?
Your density increases, but your L does not. So
Yeah, your L does not, but your A does. So half of A is now half of the illuminated area does not see any molecules anymore, so that just passes through.
So the same thing happens as before.
Not entirely.
Stays the same.
No, not entirely. Because so what happens now? Because A, so only half of the cuvette is illuminated. Only half of the cuvette sees. Sorry, the whole of the cuvette is illuminated, but only half of that light sees molecules. So half of it just passes through. That is this factor. The other half actually encounters molecules. So that is attenuated. So that will see a Lambert-Beer type of attenuation, and then again at an increased concentration. And then, of course, if you would, so this would be the transmittance, so I over I0. If you would then take the ln of that and take the and calculate the absorption coefficient from that, it would give you something that looks as ugly as this. But the point is, it is smaller than what we had when the molecules were homogeneously distributed. So the takeaway point of this little thought experiment is that it matters how the absorbing molecules are distributed. If you push them one way or push them another way, you can get different results, and it is not it's not even entirely predictable what kind of results you will get.
Question about that.
Yeah.
Where is the given a half times the comes from the half plus? Where is it?
So which
First part of the half plus.
this one?
Yes.
Yeah. Yes. So half of so we still have the same amount of light that goes into the cuvette, but since we now somehow equally split, we moved all the molecules to the side. That means that half of I0 does not see any molecules at all, but just passes through, and the other half of I0 will see molecules and will be absorbed. So then I divided by I0 would be that half time of the light that just passes through, and this half with the exponential factor behind that actually is attenuated.
Yes.
Yeah. Okay. Super. Yeah. So the conclusion of that thought experiment is that the same amount of molecules in this cuvette. You can have the same amount of molecules in the cuvette, but you can still measure a different absorption coefficient just depending on how they are, let's call it organized. And you can have that as well in tissue. Because so name one big absorber. Yeah. Water is so water actually is pretty homogeneously distributed. So that, but hemoglobin is so hemoglobin is in red blood cells. Red blood cells are in blood vessels. So it is by per definition not homogeneously distributed but organized. So you will see this in vivo as well. Okay, what I am not going to do is explain how this works. But I'm going to show. I'm going to give you on Canvas a document, a Word document, where this is explained. My homework for you is to read that, and I will start next Tuesday by asking questions about it. And then I think it's a good. It's maybe good to finish for today. Yeah.
Sounds cool.
Okay. Doe het zo.